Hey there, and welcome to this explainer. Okay, so if you're studying 10th standard math, you've probably spent, I don't know, countless hours staring at letters and numbers mashed together on a page. You know what I mean? The X's, the Y's, the squares, the cubes. Honestly, it can sometimes feel like trying to read a completely foreign language, right? But what if I told you that every single one of those algebraic expressions is actually a secret map? Seriously. Today we're going completely visual. We're going to take those standard textbook formulas, specifically polynomials, and translate them into actual shapes, curves, and roller coasters. By the time we wrap this up, you won't just know how to solve a polynomial. You're going to know exactly how to see it.
So let's just dive right into this question. Let's pull back the curtain and reveal that a graph is really just a visual map of an algebraic equation. We often get so bogged down in just moving numbers from the left side of the equal sign to the right side that we completely forget we're actually describing a physical space. A polynomial isn't just some boring hurdle you have to clear for an exam. It's actually a set of instructions for drawing a very specific, beautiful shape. When we plot these on a Cartesian plane, that grid with the horizontal x-axis and the vertical y-axis, these equations literally come alive. They swoop, they dive, they cross lines, and the points where they interact with that grid, well, that is where the absolute magic of math happens. All right, to understand these shapes, we first need to know exactly what kind of math machine we're dealing with. Think of polynomials as these little math machines with different power levels, and they're defined by their highest degree. That's just a fancy way of saying the highest exponent attached to our variable, x. So, if the highest power is just an invisible 1, like in 2x minus 3, we call that a linear polynomial. If we crank the power up to 2, like x squared minus 3x minus 4, that becomes a quadratic polynomial. And hey, fun fact, quadratic actually comes from the word quadrat, which means square. And finally, if we push our machine to a power of 3, like x cubed minus 4x, well, that's a cubic polynomial. You can think of the degree as the DNA of the equation. It completely dictates how the equation is going to behave and what it's eventually going to look like.
Now let's grab a mental magnifying glass and put it right on the equation. Let's take a quadratic polynomial, specifically p of x equals x squared minus 3x minus 4, and just start feeding it numbers. This is our math machine in action. If we drop a 2 into this machine, wherever we see an x, we get 2 squared minus 3 times 2 minus 4. If we do the math, the machine spits out a negative 6. But as we walk through substituting these values step by step, we're hunting for something incredibly specific. We are on a mission to find the magic input that outputs 0. Okay, let's try plugging in a negative 1. Negative 1 squared is 1. Minus 3 times negative 1 is positive 3, minus 4. Wait a second. 1 plus 3 minus 4 equals exactly 0. So here's the absolute crucial takeaway. A 0 is simply the magical input that forces our entire math machine to power down to exactly 0. If you plug in a number, let's call it k, and the whole expression equals 0, then k is your 0. We just found out that negative 1 is a 0 for our quadratic equation. And if you tried plugging in the number 4, you'd find that 4 squared is 16, minus 12, minus 4. Yep, that also equals 0. So for this specific polynomial, negative 1 and 4 are its zeros. In algebra, finding these zeros is basically like finding hidden treasure. It's the whole point of what you're usually being asked to solve.
Okay, get ready, because here comes our big visual reveal. We've talked a lot about the algebra, but how does all this translate to our visual map? Well, finding a 0 in algebra is literally identical to finding where a curve hits the ground level on a graph. Imagine the x-axis, that horizontal line going from left to right, as the solid ground. When your polynomial's output, its y value, is 0, you are quite literally standing flat on the ground. You have absolutely no height. You're not floating up above in the positive numbers, and you aren't buried underground in the negative numbers. Therefore, the algebraic zeros of a polynomial are the exact x-coordinates where the graph of that polynomial intersects the x-axis. This right here is the true geometrical meaning of a 0. It's just brilliant, isn't it? Let's start by looking at the simplest shape we have, the linear polynomial, written in the form ax plus b. Because its degree is just 1, it forms a perfectly straight line on a graph. Now, think about it. If you draw a straight line on a piece of paper and it isn't perfectly horizontal, it's only ever going to cross that x-axis, the ground, at exactly 1 point. So, for a linear polynomial, it hits the ground exactly once, and it's represented by this really neat little algebraic ratio, x equals negative b over a. That's simply the constant term with its sign flipped, divided by the coefficient of x. 1 degree, 1 straight line, exactly 1, 0.
Section 1. Shape-shifting, parabolas, and quadratic zeros.
Let's bump things up to degree 2, the quadratic polynomials. This is where straight lines start to bend and the math gets some really cool curvature. We're moving from ax plus b right into the world of ax squared plus bx plus c. This beautifully illustrates the exact quadratic we solved algebraically a minute ago, x squared minus 3x minus 4. Look at how the curve dips down below the x-axis and then sweeps right back up. This majestic U-shape is what we call a parabola. Now look really closely at where that curve intersects the thick horizontal line, the x-axis. It crosses at the exact x-coordinate of -1, and again at the x-coordinate of 4. It perfectly hits the ground at our magic zeros. What took us several minutes to calculate by crunching numbers is instantly visible right there geometrically.
But you know, parabolas don't just open upwards like a big smile. Depending on the math machine's inner workings, specifically if the very first number, the a term, is negative, the entire parabola will flip upside down. It ends up looking like a frown, or maybe an arched structural bridge hitting the ground. But here's the best part. The roll remains exactly the same. Wherever the legs of this arch touch down on the x-axis, those are your zeros. The geometry never ever lies to you.
Now, because a parabola is a curve, it gives us a few unique ways it can interact with the ground. Geometrically speaking, this means a quadratic equation might intersect the ground twice, like the ones we just saw. We call those two distinct zeros. But imagine just shifting that U-shape slightly up. It might just lightly touch the x-axis at exactly one single point, just its very bottom tip kissing the line, before going right back up. In that specific case, we say it has two equal zeros, but visually it's just one single intersection point. Or what if we shift the parabola entirely above the x-axis? Then it just hovers there. It never intersects the ground at all. In that scenario, the quadratic polynomial has absolutely no real zeros.
Section 2. The cubic roller coaster. Visualizing degree 3.
Okay, now we're going to crank our math machine all the way up to degree 3, the cubics, where the visual map basically turns into a roller coaster. We are adding an x cubed term, and things are about to get really twisty. Try to trace the path of this graph with your eyes. This is the graph for the cubic polynomial x cubed minus 4x. Notice how it starts way down in the bottom left, rises up to cross the x-axis, hits a peak, dives back down across the x-axis again, hits a valley, and then shoots right back up across the axis one last time. This cubic curve slithers across the x-axis exactly 3 distinct times. If you check the coordinates, they are at -2, 0, and +2. Because the curve meets the x-axis in only these 3 specific points, their x-coordinates are the only zeros of the polynomial.
But hey, just like quadratics, cubics can shift around and completely change their relationship with the ground. These side-by-side graphs brilliantly show a cubic touching the ground only once or exactly twice. Over on the left, we have the simplest possible cubic, y equals x cubed. It comes up, flattens out for just a millisecond at the origin, at 0, and then keeps right on going up. So only one 0. Then on the right, we've got x cubed minus x squared. It comes up, touches the 0 mark, dips down slightly, and then shoots back up, crossing at exactly x equals 1. So it intersects the x-axis twice. This perfectly proves that a cubic doesn't have to cross 3 times.
And that brings us to the golden rule of this whole explainer. Guys, this is a truly critical concept for your exams, so listen up. The degree of the polynomial tells you the maximum number of times it can ever hit the ground. A linear equation of degree 1 has at most 1 0. A quadratic of degree 2 has at most 2 zeros. A cubic of degree 3 has at most 3 zeros. So, zooming out, in general, a polynomial of degree n will intersect the x-axis at most n points. It is a beautifully simple, unbreakable limitation built right into the very fabric of algebra.
Section 3. The ultimate test. Counting zeros on graphs.
Okay, let's put this incredible new visual translation skill to the test with a rapid-fire challenge. This kind of stuff is taken straight from your curriculum exercises, so treat this like a little interactive game. We are just looking for ground touches, okay? Look at graph Roman numeral 1 in the top left. Trace the curve. How many times does it actually cross the horizontal x-axis? Just one intersection, so that's 1 0. Now scan down to graph number 4, that straight line on the bottom left. How many? Just one straight line hit. It's clearly a linear polynomial. Check out graph number 2 in the top middle. It's a beautiful downward-facing parabola. It crosses exactly twice, 2 zeros. And what about graph 6 down on the bottom right? It waves up and down like a snake. Let's count the crossings. 1, 2, 3, 4. This means the polynomial has exactly 4 zeros, and based on our golden rule, we immediately know it must be at least a degree 4 polynomial. Do you realize what you're doing? You are now literally reading the structural DNA of an equation just by glancing at a picture. I'm going to leave you to ponder that beautiful connection. I really hope this proves to you that math is never just a bunch of abstract numbers on a page. It's a vibrant, visual world just waiting to be explored. You now understand that finding a zero isn't just some blind robotic calculation. It's pinpointing exactly where a mathematical shape touches the earth. Keep this visual map in your head the next time you face a quadratic or a cubic equation in class. Thank you so much for joining me in this explainer, and keep exploring.
Hey everyone, and welcome to today's explainer. If you're in 10th standard and you're working through the NCERT or Karnataka Board math curriculum, you are in the exact right place. Today, we're not just going to mindlessly memorize formulas. No, we're going to look at polynomials in a completely new way. We're going to treat them not as random mathematical symbols, but almost like biological organisms that have a highly structured, hidden genetic code. Imagine walking into a science lab. What if I told you that you could predict a complex equation's final outcome, its roots, or what we call its zeros, just by glancing at the numbers attached to its variables? Seriously, no massive calculations required. Just reading the mathematical DNA. That's exactly the magic we are uncovering today. So, here is our game plan. First, the polynomial DNA. Second, cracking the quadratic code. Third, splitting the middle term. Fourth, working backwards. Fifth, level up, cubic polynomials. And finally, the grand summary. Let's dive right in.
All right, starting with Section 1, the polynomial DNA. Ingredients versus traits. I want you to think of an equation's coefficients, the actual numbers sitting right in front of the letters, as the raw ingredients of a recipe. The final results, the baked cake if you will, represents the zeros of that polynomial. But what exactly is a zero? Well, a zero is simply a real number k that when you plug it back into your polynomial, makes the whole entire thing equal to absolutely zero. And if you were to sketch this out geometrically, the zeros are the exact spots where your curve slices right through the x-axis. It is the defining physical trait of the polynomial. Let's actually look at a direct comparison. Take the simplest mathematical organism out there, a linear polynomial, shaped like ax plus b. Its single zero is strictly 100% determined by its coefficients. The zero is literally just minus b divided by a. So the physical traits are entirely controlled by the basic ingredients. But you're probably wondering, does this neat little pattern hold up for the more complicated equations? Let's find out in Section 2, cracking the quadratic code, unlocking the parabola. Okay, let's put a magnifying glass on quadratics. These are parabolas. Their highest power is 2, which means they can have at most 2 zeros. Let's call these two zeros alpha and beta. Here is their first unbreakable biological law. If you take those two zeros, alpha and beta, and add them together, their sum will always map perfectly back to the coefficients. The sum is strictly equal to the negative coefficient of x divided by the coefficient of x squared, or in simpler terms, minus b over a.
And that brings us to the second law, the product. If you multiply those exact same two zeros together, the result connects directly to the constant term divided by the leading coefficient, so simply c over a. Think about how crazy that is. These two laws mean you can know the sum and the product of the final answers before you have even solved the problem. Let's test this in Section 3, splitting the middle term, seeing the code in action. Imagine we're standing at a whiteboard with the quadratic polynomial x squared plus 7x plus 10. To find its zeros, we are going to perform some mathematical surgery by splitting the middle term. We need two numbers that multiply to our constant, which is 10, and add up to our middle coefficient, which is 7. What fits the bill? 2 and 5. So we rewrite that 7x as 2x plus 5x. By grouping them together, we factor the whole thing out to get x plus 2 times x plus 5. Setting those equal to 0 gives us our two physical traits. The zeros are minus 2 and minus 5. Now notice what just happened here. Let's actually verify this manually. If we add our zeros together, minus 2 and minus 5, we get minus 7. This perfectly exactly matches our sum formula. Remember, minus b over a, which is minus 7 over 1. And the product? Minus 2 times minus 5 equals a positive 10, which is exactly our c over a term. The mathematical DNA laws are completely, flawlessly verified. Now, what if we get a curveball? Let's look at example 3 from your textbook, where the middle term is just completely missing. We've x squared minus 3. To find these zeros, we rely on the difference of squares identity. A squared minus b squared equals a minus b times a plus b. So x squared minus 3 factors beautifully into x minus root 3 times x plus root 3. This gives us our two zeros, positive root 3 and negative root 3.
So let's run the DNA test on this one. The sum of positive root 3 and negative root 3 completely cancels out. It is exactly 0. And if you look at our original equation, our b coefficient for the middle term, it was 0. The DNA matches. The product gives us -3, which matches our c term perfectly. This just proves that this beautiful pattern is completely unbreakable, even when terms are missing. Moving on to section 4, working backwards, from traits to DNA. So here is a really fascinating question. If we only have the final physical traits of the organism, can we reverse engineer the original math DNA? Let's tackle example 4. We're given a challenge. Build the quadratic equation entirely from scratch. All we know are the traits. The sum of the zeros is -3, and the product of the zeros is 2. Can we do it? Absolutely we can. We know our sum is -b over a, which equals -3, and our product is c over a, which equals 2. To build the simplest, most basic version of this recipe, we'll just assume a is equal to 1. The moment we do that, everything falls into place. b instantly becomes +3, and c becomes 2. By plugging these right back into our standard form, we've rebuilt the entire polynomial, x squared plus 3x plus 2. We just successfully reverse engineered the math. Let's kick it up a notch in section 5, level up, cubic polynomials and scaling the logic. So what happens when we look at cubic polynomials? These are equations where the highest power is 3. A cubic is a slightly more complex organism. It has 4 ingredients now, A, B, C, and D. And because its degree is 3, it can have up to 3 distinct zeros, which we will call alpha, beta, and gamma. Because there are more moving parts here, we now have 3 distinct genetic relationships linking the zeros back to the coefficients. First, let's look at the sum. Just like with our quadratics, if you add up all 3 zeros together, alpha plus beta plus gamma, it is still perfectly anchored to -b over a. That highest level relationship, it never changes its pattern. But now we have a new middle relationship. What if we multiply the zeros in pairs and then add them up? So alpha times beta plus beta times gamma plus gamma times alpha. This links directly to the very next coefficient in line. It's equal to c over a. And finally, the grand product. If you multiply all 3 zeros together, alpha times beta times gamma, it maps strictly to the final ingredient in our cubic recipe, -d over a. If you check out example 5 in your textbook, testing these exact rules on a polynomial like 3x cubed minus 5x squared minus 11x minus 3 verifies this flawlessly. The signs even alternate, minus plus minus. It's a perfect rhythmic sequence. All right, let's bring it all together in section 6, the grand summary. The universal code. We have covered a lot of ground today, from simple straight lines to curving parabolas and complex cubic waves. But look at this matrix. The universal pattern here tells the entire story. No matter the degree of the polynomial, the DNA coefficients strictly and rigorously dictate the behavior of the zeros. The sum of the roots always starts with -b over a. The product always relates back to the trailing constants. You are now equipped to look at pretty much any polynomial in your textbook and instantly understand its underlying architecture without having to endlessly crunch numbers first. But I want to leave you with one final thought before we wrap up. We've mastered the genetic code up to degree 3 today, but math goes on infinitely. If polynomials follow such strict, beautiful, undeniable rules for linear, quadratic, and cubic forms, what kind of mathematical secrets and patterns lie hidden in degree 4, degree 5, and beyond? The code is out there, just waiting to be cracked. Thank you so much for joining me on this explainer. Keep exploring, keep questioning, and I will see you in the next one. All right, let's jump straight in. Welcome to this masterclass explainer. Look, we aren't here to relearn basic math today. You're in 10th standard, you're prepping for the highly competitive 81E or 81K board exams, so I know you already know what a polynomial is. Instead, we're completely flipping the script. Today, you and I are stepping into the shoes of a veteran Karnataka SSLC board exam evaluator. Honestly, this explainer is basically your ultimate cheat code for Chapter 2. I'm going to pull back the curtain and show you exactly, and I mean literally exactly, how the board hands out marks on your paper. And maybe more importantly, where you're throwing them away. Now, here is a harsh reality check. You could literally be a math genius. You could know the textbook inside and out, back to front. But if you don't present your answers the exact way the official evaluation scheme demands, you are going to bleed marks. It's that simple.
Evaluators, well, we have hundreds of papers to grade. We aren't really reading for your personal brilliance. We are speed scanning for very specific value points, specific steps, specific formulas. So in this explainer, we are strictly looking at official model answers and marking schemes. We're going to take that raw math knowledge of yours and convert it into maximum board exam scores. And trust me, it is way easier than you think. Let's start climbing what I call the evaluator's escalator, starting with literally the easiest marks you can grab. Okay, for those Part A multiple choice or direct one-mark questions, the board absolutely loves testing the geometrical meaning of zeros. And what happens? Students get into the exam hall, the pressure is on, they see some weird, wavy, complex graph, and they just panic. But as an evaluator, I'm giving you a massive shortcut here. Use the one-mark visual hack. X marks the spot. Listen to me carefully on this. I want you to completely ignore the y-axis. Seriously, pretend it doesn't exist. Do not get distracted by how tall or how deep that curve goes. The zero of a polynomial is literally just the x-coordinate of the point where the graph cuts across the x-axis. Period. The end. Just look at how this plays out on an actual official exam graph. You see that wavy polynomial line? An unprepared student is going to look at that and try to calculate some crazy algebraic equation in their head. But a smart 81E candidate, they just count. 1, 2, 3. The curve slices through that horizontal x-axis exactly 3 times. And what does that mean? It means there are exactly 3 zeros for this polynomial. You just count those intersections, write down the number 3, and boom. You've just bagged an instant 1 mark without doing a single calculation. It feels almost too simple, right? But you would be stunned by how many students second-guess themselves and mess this up. Let's look at another one from the official key and see what happens when the question asks for the exact zeros, not just how many there are. So we've got a parabola opening upwards. The board's key clearly states the expected answer is -1 and 4. Why? Well, because the curve crosses the horizontal line right at the x value of -1 and again at the x value of 4. Simple enough. But here is the real insider secret. If you look at the evaluation skier, the board actually awards a half mark just for identifying the -1 and a separate half mark for identifying the 4. Meaning if you rush and only write down 4, you're only getting half a mark. Precision is absolutely everything here. Every single intersection point is a half mark payout. Right, let's step it up to the algebraic battleground, the relationship between zeros and coefficients. Guys, this is heavily tested. For your standard quadratic polynomial, ax squared plus bx plus c, the sum of the zeros is always -b over a. And the product? That's c over a. But do not sleep on cubic polynomials. The board loves to throw those in to catch you off guard. For a cubic, the sum of the zeros is also -b over a. But the product of all 3 zeros is -d over a. You absolutely need to have these memorized cold, because to an evaluator, these aren't just random formulas. They are literal checkboxes on our grading sheet that unlock your very first marks in a 2-mark or 3-mark question. Okay, I want you to look really closely at this. This right here is the holy grail of evaluation. It's an actual, official, key answer from an 81E paper for a 3-mark question. The question asks to find the value of 1 over p minus 1 over q, given a specific quadratic equation. Now, scan over to that right-hand margin. Do you see all those little 1/2 fractions stacked up? That is exactly how we evaluators distribute your points step by step by step. The board is incredibly generous if you show your work, but they are completely unforgiving if you decide to skip steps in your head. Let's break down that exact marking matrix line by line so you see the magic happen. The very first thing the student does is simply write out a equals 1, b equals -3, c equals 2. Just doing that and plugging it into the sum formula gets you your first half mark. Boom. Then, calculating the product, c over a, which gives you 2, that's another half mark. Next, they just take the lowest common multiple of the expression in the question, getting q minus p over pq, another half mark. You haven't even touched the heavy, complicated algebra yet, and you've already banked 1.5 out of 3 marks, all because you clearly stated the coefficients and the basic formulas. See? This is exactly what I mean when I say you have to write the paper for the evaluator. Now, here comes the tragedy, the absolute most common trap students fall into right here. I literally see this hundreds of times a day when I'm on evaluation duty. Remember, the formula for the sum of zeros is -b over a. In the equation we just looked at, b was already a negative number, -3. The official key answer handles this perfectly. It explicitly writes out the negative sign, opens a bracket, puts the -3 inside, closes the bracket all over 1, which gives a +3. But the student trap? They are rushing, They see the -3 in the equation, they completely forget about the negative sign built into the formula itself, and they just write -3/1. And just like that, in a split second, that half mark is gone. And because your sum is wrong, your entire 3-mark calculation is going to collapse like a house of cards. Always, always write out the double negative. Which brings us to another massive, heartbreaking trap, especially in those 2-mark questions where they ask you to actually form a quadratic polynomial when they give you the sum and product. The correct official standard form is x squared minus the sum of zeros times x plus the product of zeros. Did you catch that? Minus the sum. The huge mistake students make is throwing a plus sign in there instead. Look, swapping that 1 minus for a plus completely ruins the final equation, and the board explicitly trains us evaluators to zero in on that exact mathematical operator. If you get that sign wrong, you lose the final mark, even if your sum and product calculations were totally flawless. Okay, shake off those algebraic traps. Take a breath, because we are escalating to the absolute climax of the polynomials chapter, the 4-mark quadratic graph. This is not a drill, guys. This is a guaranteed, heavyweight question that can single-handedly save or boost your grade. We are going to conquer this right now. But listen, treating this 4-mark graph like it's just a fun little drawing exercise, that is a fatal error. The board has a brutally strict, uncompromising blueprint for how these 4 marks are awarded. Let's look at it. Here is the official 81E grading rubric for that 4-mark graph. You need to burn this into your memory right now. Step 1, the table. Generating the correct x and y coordinate table is worth exactly 2 marks. That means literally half of your points are secured before you even pick up a pencil to draw a single line. Step 2, drawing the parabola. Plotting those points accurately and drawing a nice, smooth curve gets you 1 mark. Step 3, identifying the roots. Explicitly writing down your final answer is worth the last 1 mark. 2 plus 1 plus 1 equals 4. Skip any of these distinct steps and you are waving goodbye to a perfect score. Let's look at the anatomy of a perfect, full score graph. This is a flawless, board-approved answer straight from the key. First, check out the table at the top. The student carefully calculated the y values for x ranging from -3 to 3. Boom, 2 marks safely in the bank. Now the graph itself. The axes are clearly labeled x, x prime, y, y prime. And look at the top right corner. The scale is explicitly written out. X-axis 1 centimeter equals 1 unit. That is exactly what we want to see. The points are plotted perfectly, and they are connected with a smooth, continuous freehand curve. No jagged ruler lines here. That smooth parabola secures the next 1 mark. But here is the insider secret about the most painful pitfall of all. I call it the tragic trap. A student will spend 10 solid minutes meticulously calculating that table. They plot the points perfectly. They write the scale. They draw an absolutely gorgeous parabola. And then they just stop. They put their pencil down and move to the next page. But to get the 4-mark finish, you have to go to the bottom of that graph and explicitly write roots are x equals -1 plus 2. If you stop at just drawing the picture, you get 3 out of 4 marks. You are literally throwing away 25% of the question's value simply because you forgot to state the final answer. I really want you to remember this phrase. The parabola is just the vehicle. The roots are the destination. The exam didn't ask you for a pretty drawing. It asked you to solve the equation graphically. The graph is literally just a tool you were using to find where the curve cuts the x-axis. Once you find those intersection points, like the -1 and 2 we saw, you have to declare them. Writing roots are x equals -1, 2 is how you signal to the evaluator, hey, I actually understand the geometrical meaning of zeros. That single sentence is what unlocks that final glorious 4th mark. So, the crucial question we are ending on today is this. You know the math, sure, but are you actually ready to write the paper the way the board wants to read it? When you walk into your mock exams and eventually sit down for that final 81E SLC paper, I want you to channel this evaluator's mindset. Double-check your negative signs, write out your step-by-step substitutions to farm every single half mark, and never, ever turn the page on a graph without writing down its roots. Stick to this blueprint, sidestep those mark traps, and you aren't just going to pass polynomials, you are going to absolutely crush it. So next time you're doing a practice paper, ask yourself, am I just doing math right now, or am I writing exactly what the evaluator wants to see?